Hello everyone, my name is Zhenjie Wu. I'm a PhD student from UC Berkeley. Today, I'm going to present our work, Integrating Domain Knowledge with Deep Learning Models, an interpretable AI system for automatic work progress identification of NATM tunnels. The research team for this project is Yuji Fujita from Anzan Corporation, Japan, and myself, under the supervision of Professor Kenichi Soga. The content for this presentation is listed the following. We start with introduction and background, then I'll give a talk about our methodology. Then I'll walk you through our implementation details, talk about our results, then end with a conclusion. The research focus for this study is about the new Austrian tunneling method, or NATM method. It is widely adopted in short-range tunneling construction process. The NATM method has two distinct features. One is cyclic, the other is sequential. Being cyclic means the construction process can be decomposed into individual construction cycles, and sequential works can be performed for these cycles. In this study, we focus on one typical NATM process, shown by this figure. We start with excavation, marking, then we do profiling to check the excavated condition. After that, we do short grid bolting to stabilize the tunnel. And if something strange happens, such as work shift or work rest, or maybe some accidents, we go to this others phase. Every construction process has a plan, but the actual work may deviate from the plan. To compare the plan with work, we need to have the project monitoring record. Currently, there are two ways of making such record. One is through this manual data entry method. So project manager or project worker will record construction process on a notebook or on iPad. However, human like myself often make mistakes, especially for repetitive tasks like this. So this method is error-prone. To remove subjective error, we can design a wireless mesh network. If the system is well designed and carefully installed, the result might be very accurate, but even for installation, it costs extra money, so this will add some extra cost to the project. Luckily, there is one powerful sensor available for almost all construction sites. That is the CCTV surveillance camera. It records almost all the on-site activities, but in a relatively unstructured way. Can we use such unstructured vision data to help us to build a system that can reduce subjective error, but in a relatively inexpensive way? The answer is yes, and we are going to use a method called deep learning-based computer vision method. I'll give a very brief introduction about this method. So in computer vision community, they use a model called convolutional neural nets to automatically extract vision features from the input image and use these extracted features to identify the semantic meaning of this image. For example, considering the figure on the left, we can use this model to identify the cats and give a location for the cats in this image. The same algorithm, with some modifications of course, can be used to power the self-driving car on identifying objects on roads. In this study, we want to use a similar technique to help the NATM automation by automatically generating the construction process record from the CCTV modeling of CCTV video. Here is how we do it. First, we need to have some prior knowledge about this NATM process. Specifically, we want to know the equipment to work relationship, which means what kind of equipment is used for different work types. We also want to have a knowledge about the time to work relationship. because NATM work is sequential and each work has an expected duration. So it is reasonable to expect certain work to be performed at a specific time. Then we need to make observations because that's the only way to know what really happened during the construction. To do that, we use these two CNN models to make the observation. One make preliminary guesses from the recorded scene, and the other find all the equipment inside the captured image. At the end, we combine all the information we have, which is the prior knowledge and observations, to predict the NATM workflow from the recorded image using the Bayesian method. The first step of our framework is domain knowledge selection. So there, as I said in previous slides, there are two different kinds of knowledge we have. The first is the time-work relationship, which describes the engineer's guess on what work will be performed at a certain time inside one work cycle. The other information we want to have is the equipment-work relationship. We will summarize it as an on-off table. If one work needs a certain equipment, then this equipment will be marked as 90%. However, we also mark all the non-used equipment with 10% probability of being observed from the monitor, because in some cases, this equipment might just park there and do nothing, but may be captured by the monitor. Step 2, we sample the video with 5 minutes interval. In this way, we reduce the problem complexity. We also compress the data, so we have a better computation efficiency. The reason for us to choose 5 minutes is that this is a very safe time interval, so we won't miss any work type inside any work cycles. This is because the minimum work duration for a certain work type is around 10 minutes. So with using 5 minutes, we'll at least have 2 images for one work type. Step 3, we use CNN models to make preliminary guesses and do equipment detection. Considering the image on the right, first we use one model to make a preliminary guess on what kind of work type is performed inside this image. So in this case, we are 83% confident about it is a short click process. Then we can also identify all the appearing equipment inside this image, which is erector, mixer, and shovel breaker. Then we need to extract all the work cycles from the time-stepped image sequence. To do that, we extract the time slots between 2 consecutive excavation marking phases. This is because every work cycle always starts with excavation and marking, because that's the meaning of tunneling. You have to excavate first, then do all the cleaning stuff. Step 5, we combine all the information we have using a Bayesian method to make final prediction, which is the left-hand side on this equation. So the goal is to know the probability of being at work at a certain work when time and equipment is given. So the time is given by the video sequence and the equipment is detected by our CNN models. And on the right-hand side, we have all the prior knowledges, which is summarized by step 1. And the denominator of this equation is a Bayesian constant, which we assume to be constant for all the work cycles. The last step is to do anomaly detection. So we want to find all the abnormal behaved cycles. And what is an abnormal cycle? If the observation does not match expectation well in a work cycle, then it is an abnormal cycle, which is shown by this figure. So what's the abnormal thing about this figure? We expect bolting at the end of the process, but there is no bolting. So we have very low probability for this time range because our prior knowledge tells us that there will be a bolting. And based on this information, we can mark this process as an abnormal cycle. Before I proceed to show our final results, let's take a look at the dataset we are using. We use 3 different sites for training, which consist of 28,000 labeled images. We use another different construction site for testing, which has around 6,000 labeled images and 12 abnormal cycles. Here are the training history for our CNN models. Recall that we have 2 different CNN models. One is the work type classifier, shown by the figure on the left, and the other is the equipment identifier, shown by the figure on the right. The x-axis is number of epochs we used for training, and y-axis is model performance accuracy. Both models reach a very high training accuracy, but there is a performance gap between training dataset and testing dataset for work type classifier. This is because work type for NATM is a rather abstract idea, so model trained on the training dataset is overfitted and does not perform very well on a different construction site, which is a training dataset. However, for equipment detection, because equipment is a rather concrete idea, so there is no such semantic gap, so the performance for the model on the testing dataset is pretty accurate as well. The workflow identification results using our framework is very accurate, as shown by this figure, which has our prediction results on extracted cycles. The x-axis is the in-process time, and y-axis is the work type inside one work cycle. The blue line is our ground truth. The green dots are the results from CNN models only, which serves as a baseline model, and the red line is the final results from our framework. As you can see, our framework performs much better compared to the CNN only case because our prediction matches with ground truth much closer compared to the CNN model. Our framework also gave abnormal scores for each detected cycle. For the first 2 cases, because this is a rather standard workflow, we gave a low abnormal score. But for the last one, there is no bolting inside this process, so we gave a high abnormal score and marked this as an abnormal cycle. Our framework is robust on the choices of prior knowledge. We use the CNN prediction model as the baseline and compare the results with our framework of different prior knowledge settings. For the first case, we're considering the Bayesian method with uniform time work relation, which is the second row in this table. Uniform time relation means that we have no time preference for work types. In other words, we are only using equipment information for the identification process. Even with this simple setting, we have around 4% accuracy boost compared to the baseline model on normal work cycles. If we change the relationship to a more realistic one, we will have around a 13% increase in total for normal work cycles. However, we don't have significant improvement on abnormal cycles because that violates our assumption for the model. But we gave high abnormal scores for such cycles, so people can expect and interpret them as they are the sources for work plan deviations. In this work, all the abnormal cycles are detected by our framework. In total, our framework gives around 10% accuracy boost compared to the baseline model. In summary, we developed an AI framework that can automatically identify NATM works from site monitoring videos, and we use AI models for observation, summarize the prior knowledge to account for field expertise, then use Bayesian method to combine all the information together. The framework is tested on a real project and shows a very accurate, around 83%, and robust against prior knowledge variance. That's all for our presentation. Thank you so much for your patience.